Hello, dear. Hello, dear students. Welcome back to the series of lecture series on major theory with course code MMTC 202. Today, in this lecture, we will discuss the integral of a step function. Integral of a step function. Okay. So, integral of a step function. Let phi be a step function with standard representation. Let phi be a step function. Let phi be a step function. Phi be a step function with standard representation. With standard representation, phi is equal to summation I runs from 1 to n ai, characteristic function of ai. Then the integral, you can say Lebesgue integral, then the Lebesgue integral, or simply the integral, you can say. Then the Lebesgue integral of phi is defined by I of phi is equal to, or you can also write the integral of phi over the major space x over x, integral of phi over x, integral of phi over x is equal to summation I runs from 1 to n a I mu star of a I. So this is the natural way to define the integral of a step function, as in the previous lecture I have explained it for some of some particular function. Okay, so this is the natural way actually to define the integral of a step function. Now, in the next theorem, we will see that this integral is actually the linear operator. So next theorem, it is the linearity of the integral theorem. That is the linearity of the integral defined above. Linearity of the integral. So next theorem is the linearity of the integral. It states that if phi and psi are step functions, if phi and psi are step functions, then integral of alpha phi plus beta psi is equal to alpha times integral of phi plus beta times integral of psi, where for all alpha, beta belongs to R. They are real numbers. Okay. So that's the linearity of the integral, linear property of integral of a step function. We first verify that integral of alpha phi is equal to alpha times integral of phi. We first verify this, where this alpha belongs to R, where alpha is a real number. So let me first verify this. So since phi and psi are step functions, so let's say let phi is equal to summation I runs from 1 to n ai characteristic function of ai, and psi is equal to summation j runs from 1 to m bj characteristic function of bj, be the standard representation of phi and psi, the be the standard representation of phi and psi. Then we will try to find the standard representation of alpha phi. Then alpha phi, what's alpha phi, is equal to summation alpha times ai, I runs from 1 to n into characteristic function of ai, be the standard representation of be the standard representation be the standard representation of alpha phi. So therefore what will be the integral of alpha phi as already defined here. If this is the standard representation of phi, then its integral is equal to the summation I runs from 1 to n ai. Ai is the real number times the measure of this set mu star of ai. Now in our case alpha phi, the scalar, the real numbers are alpha ai and the set is ai. So therefore the integral is therefore integral of alpha phi is equal to summation I runs from 1 to n alpha ai times mu star of ai. So this is equal to alpha times summation I runs from 1 to n ai mu star of ai, and that's equal to alpha times integral of phi, because as integral of phi is equal to, by definition, as integral of phi is equal to summation I runs from 1 to n ai mu star of a. This is the integral of phi. So that means integral of alpha times phi is equal to alpha times integral of phi. So therefore it is now sufficient to prove that integral of phi plus psi is equal to integral of phi plus integral of psi. Therefore it is sufficient to show that integral of phi plus psi is equal to integral of phi plus integral of psi. Okay. Now this is phi and psi are step functions, therefore their sum is step function. Since phi plus psi is a step function, since phi plus psi is a step function, since phi plus psi is a step function. So therefore, let this be its standard representation. Let phi plus psi be equal to summation k runs from 1 to r ck into characteristic function of ck. So this is k here, ck. B and therefore and this b and let phi b, and this phi b be the representation of this summation, be the representation of standard representation of phi plus psi. Okay. So therefore, what will be the integral of phi plus psi? Therefore, integral of, by definition of step function, integral of a step function, it's equal to summation k runs from 1 to r ck mu star of ck. So that's this. We need to show that this sum is equal to integral of phi plus integral of psi. That's what integral of phi is equal to summation I runs from 1 to n a I, and this is here k runs from k is equal to 1 to. Okay, so therefore we show that this summation k runs from 1 to r ck mu star of ck is equal to summation I runs from 1 to n ai mu star of ai plus summation j runs from 1 to m bj mu star of bg. So this is let me write this as star. So this we have to prove actually. Integral of phi plus psi is equal to integral of phi plus integral of psi. So to prove this, let me define the following sets first. So let's define the following sets here. Let's define E, which is equal to the double union. Let E be equal to this set union I runs from 1 to n ai, then union j runs from 1 to m bg. Then you can see this E is a finite measure. Then mu star of E is less or equal to the summation I runs from 1 to n mu star of ai plus summation j runs from 1 to m mu star bj. Both are finite. It's a finite sum. It's a finite sum because it is the sum of finite numbers. Finite sum of finite numbers. It's obviously finite. So measure of E is actually finite. It's a finite number. Next, we put we put the set A naught, which is equal to the E minus union of AIs, E minus union I runs from 1 to N AI, and set B naught is equal to E minus union I runs from 1 to, sorry, it's J runs from 1 to M BG. Let's define these two sets and also put and take these two numbers and take A naught is equal to B naught is equal to 0, is equal to 0. Then these AIs, I runs from 0 to N and BJs, J runs from 0 to M, they are disjoint. So this is simple because what's this A naught actually? AIs are already disjoint in the standard representation. These sets are disjoint. I runs from 1 to N AI, they are all disjoint sets. And A naught is disjoint from this union. I runs from 1 to N AI. That means A naught is disjoint. A naught is disjoint from each AI actually. I runs from 1 to N. So it means that these AIs for I varies from 0 to N, they are disjoint. And similarly, BJs, because it is the standard representation of the function psi, these BJs are disjoint sets in the standard representation. J runs from 1 to M, and this B naught, it's a disjoint from each BJ. J runs from 1 to M. So that means BJs, where J runs from 0 to M, they are also disjoint. So then AI and BJ then AIs and BJs are disjoint, are disjoint, where this I is equal to 0 to N and this J is equal to 0 to M. J is equal to 0 to M. So these AIs and these BJs are disjoint. So they are not disjoint with each other. This should be clear here. AIs and BJs are not disjoint with each other. Okay. AIs are disjoint with AIs only. Okay. And BJs are disjoint with BJs only. So this should be clear here. So actually I should write here this. AIs are disjoint and BJs are disjoint. That so they are disjoint. They are not disjoint with each other. AIs and BJs. Okay. Next, we see that now this union I runs from 0 to N AI, it's same as the union J runs from 0 to M Bj, which is equal to E. It is a very simple. Let me verify this. This set is equal to E. Okay. Let me verify this. So we have this union I runs from 0 to N AI, which is equal to A naught union I runs from 0 to N 1 to N AI. And what's A naught? By definition, A naught is equal to E minus union I runs from 1 to N AI. Then I will take again this union I runs from 1 to N AI. So first I am removing this union from the set E, then again I am adding this union. Okay, so it's equal to E actually, you can see. It's E. Similarly, union J runs from 0 to M Bj is equal to E. So that's very simple, that's not too hard. These unions are equal and they are equal to E. Now, for the step function phi plus psi, I define the set C naught. Okay. So first of all, I will see this. Since our function 5x plus psi x is not equal to 0, 5x plus psi x, since this value, since 5 plus psi of x, which is equal to 5x plus psi x not equal to 0, implies either not equal to 0. If this some function is not equal to 0, this implies phi x not equal to 0 or psi x not equal to 0. So whenever phi x plus psi x is not equal to 0, it implies either phi x not equal to 0 or psi x not equal to 0. But in case they are equal, this sum may be equal to 0, but suppose it's not equal to 0, then it will assume of one of the values, one of the non-zero values, C1, C2, so on up to C, or in case it's not equal to 0. So because we have a standard representation of for 5 plus psi is equal to union, sorry, it's not the unit summation, k runs from 1 to r, then ck characteristic function of ck. This is the representation of phi plus psi. So in case its value is non-zero, so the value must be either c1, c2, or cr. So it's one of the values of ck. And at that moment, this either phi x not equal to 0 or psi x not equal to 0. So from this we conclude that it follows that. So therefore it follows that union union k runs from 1 to r is subset of e. Is subset of e. So let me verify this, how it's subset of e. So let's choose a point. Choose x belongs to union k runs from 1 to r. So this implies x must be in some ck, x belongs to ck for some k and for exactly 1k exactly. This whenever x belongs to k, this means phi x plus psi x must be equal to k by its definition, by it's equal to ck, small ck, which is not equal to 0. So that means either phi x not equal to 0 or psi x not equal to 0. This means phi x is equal to some ai or psi x is equal to some vg, because these are the non-zero values for some I and j, for some I and j. But whenever phi x equal to ai, it means that x belongs to capital AI, and whenever psi x belongs to bj, it means that x belongs to capital Bj. So this means x belongs to ai or x belongs to Bj. So that means x belongs to union I runs from 1 to n, ai, union j runs from 1 to m, bj. That means this x belongs to e, because this double union is equal to e. So thus this union ck thus union ck k runs from 1 to r is subset of e. So this is very important relation. We will use this relation. Okay. Next, we define sets C naught as we had defined sets for A, I, and BI. Now we define the sets for this CK. we define this set, put C naught, which is equal to E minus union K runs from 1 to R. K runs from 1 to R. And take the scalar C naught is equal to 0 and take this number C naught, small c naught, which is equal to 0. Then again these Ci's are pairwise disjoint, as I have already explained. The sets Ai's and Bi's are pairwise disjoint. Then Ci are pairwise disjoint. They are pairwise disjoint. Now we verified that. Now we verify that this set Ck, it's equal to the double union I runs from 0 to n union j runs from 0 to m Ck intersection Ai Ck intersection Ai intersection Vj. This is intersection. Okay. So to verify this, let me expand this union here, and I will show that after expanding this union, I will prove it's equal to Ck. So we have this we have the double union I runs from 0 to n union j runs from 0 to m then Ck intersection Ai intersection B J. This is equal to, you can see this is equal to this union I runs from 0 to n. Then I will put this union here because Ai's are independent of J and Ck is also independent of J. So I can move this union J runs from 0 to m to here. Okay, it's equal to Ck intersection Ai intersection union J runs from 0 to m Bj. That's equal to union 0 to n Ck intersection Ai, and this is intersection because this union is already done. It's equal to E. Now this union it's equal to Ck intersection union I runs from 0 to n Ai intersection E, and this is equal to Ck intersection E, that's this E here, intersection E, and that's equal to Ck intersection E, but we know that union Ck is subset of E. So that means each Ck is actually subset of E, which implies that Ck intersection E is equal to Ck. So therefore this union is actually equal to Ck. It's equal to Ck. And they are also a disjoint for 0 less or equal to k less or equal to n, these Ck's. So thus mu star of mu star of Ck, which is equal to mu star of union I runs from 0 to n union j runs from 0 to m Ck intersection Ai intersection Bj. So what's this? Since the union is disjoint, and they are actually here intersection is so these unions are disjoint. It's a disjoint. Okay, this each ck is a disjoint union. So it's equal to double summation I runs from 0 to m and summation j runs from 0 to m. This is mu star of ck intersection ai intersection bj, mu star of ck intersection ai intersection bj. So next we verify that next we verify that the small ck times mu star of ck intersection ai intersection bj, it's equal to ai plus bj times mu star of ck intersection ai intersection bj. So we verify this. So in case this set is empty set, in case this set is empty set, then mu star of the empty set is 0. So in that case, this number will be equal to 0, and also this is also equal to 0 because this is the empty set. Therefore, mu star of the set is 0. So both the sides are equal to 0. So in case the set is empty, the equality holds. These two expressions, these two numbers are equal actually. So if the set is empty, if ck intersection ai intersection bj is empty, then both the sides then both the sides are equal to 0. So now now let's take the point in the interest. Suppose this is not empty set. Let's take x belongs to ck intersection ai intersection bj. So this implies that x belongs to ck and x belongs to ai and x belongs to bj. Whenever x belongs to ck, it means that phi plus psi of x is equal to small ck. But whenever x belongs to ai, it means that phi of x is equal to ai, and whenever x belongs to bj, it means that phi of x is equal to bj. So thus this ck, which is equal to phi x plus psi x, thus the ck, which is equal to phi x plus psi x, it's equal to ai plus bj. So ck is equal to ai plus bj. This implies that ck times let me multiplying throughout by this mu star of the set ck intersection ai intersection bj, it's equal to ai plus bj times the mu star of ck intersection ai intersection bj intersection bj. So these two expressions are equal actually. Now we use these things that we already derived in this theorem to prove our main result. So let me prove this. And using the finite additive property of mu star also, on the class of measurable sets, because here the sets are all measurable. CK, AIs, and BJs, they're all measurable. And we know that the outer measure is a sigma additive or finite additive on the collection of measurable sets. So now let's try to prove our main result. Now integral of phi plus psi. By definition, this is equal to summation k runs from 1 to r ck times mu star of ck. But this ck is the double union. It is already done. What's the ck? You can see here. This ck is something. It's double union. I think. Okay. This ck here. You can look at this. This ck is equal to the double union. I runs from 0 to m. J runs from 0 to m. Ck intersection ai intersection bj. So let me substitute this value there. Oh, it's equal to summation k runs from 1 to r, or you can directly apply this ck times mu star of ck intersection ai intersection bj is equal to ai plus bj mu star of ck. Okay, this can also apply this ck times mu star of, okay, so I cannot apply here that result. So let me apply this that union ck times this is small ck, okay, ck times ck times mu star of ck. It's here now mu star of the double union I runs or I can directly apply that expression here. Sorry, let me apply this one directly. Okay. So here I have this. Here I have summation k runs from 1 to r ck mu star of ck. Let me see what's this mu star of ck actually. Mu star of ck is this one. What's mu star of ck? It's a double sum mu star of ck intersection ai intersection bj. Apply this expression. Okay, this equation here. So it's equal to summation k runs from 1 to r. In this one, into mu star of ck, mu star of ck, it's equal to the double sum. It's equal to summation I runs from 0 to n, and summation j runs from 0 to m ck times mu star of ck intersection ai intersection bj intersection bj. So it's you can see this at page number, this one, page number 14. This is done mu star. So if I will if I will write this as 1, I will write here by 1. Okay, by 1. Now this double sum, this ck mu star of ck intersection ai intersection bj, it's equal to ai plus bj. So it's equal to summation k runs from 1 to r summation I runs from 0 to n, and summation j runs from 0 to m. Then we have ck times not ck. I will replace this ck by ai plus bj because it's already done. It's equal to ai plus bj times ai plus bj times mu star of ck intersection ai intersection bj. By this, let me write that expression. Right, that this is 1 by second. I can write. Let me name this as second. So here I will write by second. Okay, by second. by second. This ck times this, oh, okay, ck. Here it is this ck times that, and that ck is equal to ai plus bj. Okay. So now it's summation k runs from 0 to r first. 0 to summation k runs from 0 to r. That's equal to okay. This is a summation k runs from 0 to r. So let me expand this sum first with respect to k. So it's equal to summation I runs from 0 to n, and summation j runs from 0 to m, ai plus bj times summation k runs from 0 to r mu star of ck intersection ai intersection bj, and that's equal to summation I runs from 0 to n, summation j runs from 0 to m, ai plus bj. This summation, because ck's are pairwise addition, it will be the union. It's mu star of the union with respect to k, union ck. K runs from 0 to r. Then I have intersection ai intersection bj. But this union k runs from 0 to r, ck is equal to e, and each ai is subset of e, bj is subset of e. So this intersection is also subset of e. So it is just equal to ai intersection bj, because these ais, they are all subsets of this union. Bj is also subset of this union. So this is equal to the summation I runs from 0 to r, 0 to n, and summation j runs from 0 to m, ai plus bj, times it's then mu star, okay, mu star of ai intersection bj. So this is equal to, let me take the product here now, it's summation I runs from 0 to n, summation j runs from 0 to m, ai times mu star of this ai intersection bj plus the double sum plus summation I runs from 0 to n, summation j runs from 0 to m, bj times mu star of ai intersection bj. And this is equal to here, let me move this ai to with this sum, because it's this ai is depends on only I, not on j. So I can write this as summation I runs from 0 to n ai into this sum, summation j runs from this sum will be equal to, because bj's are pairwise disjoint, summation with respect to j can be written as mu star of the union with respect to j. So I can write this as like this, mu star of ai intersection union j runs from 0 to m bg, okay. Then plus here this sum, second sum, it's first I will this sum I will expand this sum, I will write this summation j runs from 1 to m as it is, summation j runs from 0 to m bj, and this summation I runs from 0 to n can be written as mu star of the union. mu star of the union I runs from 1 to n, I runs from 0 to union I runs from 0 to n a I intersection bg. This summation j runs from 0 to m bj mu star of union I runs from 0 to n ai intersection bg. Okay, and this is equal to summation ai I runs from 0 to n into mu star of ai intersection that union is equal to e plus summation j runs from 0 to m bj mu star of the union with respect to I, that's again equal to E intersection Bj. But AIs are subs, each AI is substub E and each Bj is substub E. So therefore, this is equal to summation I runs from 0 to n AI mu star of AI plus summation j runs from 0 to m Bj mu star of bj. Since a naught is equal to 0 though, so this sum can be written as I runs from 1 to n because first term is equal to 0, and the first term of this sum is also equal to 0, so this can be written as summation I runs from 1 to n a I mu star of a I plus summation j runs from 0, sorry, it's 1 to m now, not 0, 1 to m, j runs from 1 to m bj mu star of bj, and that's equal to integral of phi plus integral of psi, integral of phi plus integral of psi. So that proves the theorem completely. And from this theorem, we can see that this integral is actually independent of the representation of a function. So that's the next theorem. Integral of a step function is independent, is independent of its representation, of its representation. Proof. Suppose phi has two representation. Suppose phi is equal to, suppose this is the standard representation. I runs from 1 to n ai, characteristic function of ai, and suppose this is the another representation, say summation j runs from 1 to m bj, characteristic function of bj. Okay, then by previous theorem, then integral of phi plus phi, which is equal to integral of phi plus phi. This implies this is integral of twice phi, which is equal to integral of phi plus integral of phi. So I will use two representations for the function phi. Here we have integral of phi plus integral of phi. So let's take this integral of phi with respect to this representation and take this integral of phi with respect to this representation. Okay. So then you can see that this is I can pull out this 2 from this integral. Okay, I can write this as twice integral of phi is equal to integral of phi plus integral of phi. So these two are not equal in general. So because this integral is with respect to this representation and this integral is with respect to the another representation. So this is a Okay.